Good morning, good afternoon, good evening, everyone. My name is Lindsay Florius, and I'm an associate scientist here at Pumas AI. I am joined by Dr. Jose Staropoli, our lead of training and education. And today we're going to be giving a webinar on parametric time to event models. If you're not familiar with, if it will share my screen, if you're not familiar with us here at Pumas AI, we engineer solutions that empower those from the front lines of healthcare from discovery to delivery. We have two main products, Pumas, which is our analytical pharmacometric software. It's an all-in-one software designed to guide you through your workflows. We also have Live, which is a clinical decision support software compatible with Epic. So today we're going to focus on Pumas, our accelerated drug development software. It is the fastest end-to-end pharmaceutical modeling and soft simulation platform for quantitative analysis across the drug development lifecycle. Some things I'd like to highlight about it are we are validated against other industry standard softwares. We are a one-stop shop, meaning that you can do your data wrangling, all your plotting, all your modeling, all in one. We are accepted by submission through the US FDA. Multiple different companies have used us. We are super fast. We are scalable for high performance computing because we are backed by Julia Computing. And we also integrate scientific machine learning. We have some things in the back end that will be coming forth very soon. As I said before, I am joined by Dr. Jose Staropoli, who will kind of give you the theory, and later I will dig deep into the code. So with that, I would like to give this back to Dr. Staropoli.
Thank you, Lindsay. Welcome, everyone. So let's talk about time to event models. I'm gonna share my slides here. I think you guys are seeing everything. Yeah. So this is what we are going to do, a brief 20-minute presentation on kind of the technical or theoretical underpinnings of time to event. I will share some resources. I will also tell you about, let me see if this works. So it's not working. Okay, so can you guys see my my laser point? Yes. So I'm gonna briefly talk about resources, say what are the different time to event analysis that we have, what is the so ubiquitous survival function, what probability distributions can we do, can we use to model our underlying survival distribution, and different approaches to TT analysis and the reference for these slides. These will be available after the workshop, will be sent to your email inbox along with the code that Lindsay will showcase after this. So some nice resource for you to check. We have 3 textbooks that are really interesting. We have the classical Collet, Modeling Survival Data in Medical Research, is a real good book. And we have more classicals, one like Smith, Analysis of Failure and Survival Data. It's a very good book. It's 20 years old, but it's a very good book. We also had another 20-year-old book called Bayesian Survival Analysis, Ibrahim, which is very nice for you to get a grasp of the probabilistic assumptions underlying those time to event models, because it's coming from a Bayesian perspective. And also there's a fun paper. It's from 2019. It's from Saleh. It's a statistical reliability analysis for a most dangerous occupation, Roman emperor. So it's a survival analysis of the different people that took the role as Roman emperor in history. It's one of the most dangerous occupation. The expectancy of life is not so great, but it's a fun paper that is a serious survival analysis with a fun context. So it's a fun paper. These are my resources. So what is time to event analysis? So it's kind of an umbrella term. It's an umbrella class of statistical methods. they all have in common that the outcome variable of interest is time. So it's time to something happen, either time to failure or time to death or time to a certain repeated event like vomit, nausea, pain, seizure. Uh, so that is what time to event encapsulates. And we are mostly interested in the occurrence or timing of this event, either being a single event or a repeated event, like vomiting, nausea, or seizure. So that's the idea. And uh, the main protagonist in a time to event analysis is our survival random variable. And what is survival random variable? Is pretty much a random variable that is constrained to the positive domain. And in the literature, most of the time they say that is T, capital T, because it's a random variable. So we call all random variables capital. So capital T is pretty much in the domain from zero inclusive until to positive infinity non-inclusive. So that's pretty much what the survival random variable is. And that brings us to the survival function. So the survival function, let me just grab my pencil here. So the survival function is pretty much one minus the cumulative distribution of our survival random variable P. So if we express that in mathematical terms, being more precise, capital F is our CDF, our cumulative function. This is pretty much the probability of certain variable, random variable T being less than T. And how do I reset this? I think it's 0. Oh, I don't know how to reset this. So bear with me. So that's our survival function, our um, cumulative function, and if we go to the survival function, that's ST, that's one minus the CDF, that's one minus this capital F function, which pretty much evaluates to this integral here. So that's the mathematical terms of the survival function. And we have this notation here that ST is a survival function of the survival random variable T at a value of this random variable T equals little t, we equals some certain time that you want to evaluate. So that's the relationship between survival function, survival random variable, and the probability concepts of cumulative distributive function. So that's our survival function. And what is the shape of the survival function? Uh, it has the following property. It is a monotonic decreasing function, which will tend to zero as time goes to infinity. And generally, it's an exponential decay function. So this is some sort an example of how your survival function uh, might be shaped. So it kind of has this exponential decay shape where it tends towards zero in as times goes to infinity. And our hazard function, that's another concept that I need to introduce. Those concepts will be displayed in code and in our Pumas model. So the hazard function generally is denoted as lambda or just h for historical reasons. And the definition is the event rate at time t conditional on survival time until time t or later. So that's pretty much the probability, uh, the probability of survival of you having an event at certain time t condition that you survive it until that time t or later. So that's the idea. And this hazard function can be described mathematically as a limit as this delta t goes to 0. This delta t goes to 0. So that's the idea. And then you have the probability of you having an the probability of you having an event at time t less than or equal than t and less equal of t plus delta t, all divided by dt times survival function at time t. So that's the idea. The kind of, you can unplug this, you can do a little bit of manipulation. This evaluates to the FT, where F is the PDF divided by survival function. We know from the previous slides that the survival function is 1 minus the CDF. So then the third line is 1 minus the CDF, and then you can pretty much say that the hazard function is the PDF divided by 1 minus the CDF. So that's the idea here. And we can also use distributions to model our survival functions. So this PDF here and this CDF here, they of the survival function, they can be modeled as distributions. So that is what we call parametric time to event. And this introduces some assumptions, but also makes a nice approach strategy for you to model time to event. So there's a wide list of candidate distributions that you can use, but most used ones are three: exponential, which is just has one parameter, lambda, because the exponential distribution has one parameter, only lambda, which is generally called the rate. You have the variable, which is parameterized by k and lambda, which are called the shape and the scale respectively. So k is the shape, lambda is the scale. And we also have the converts distribution, which is parameterized by eta, and beta also sometimes is just called b, which eta is the shape and b is the scale. So you can use more distributions, but most of the time you'll be using one of those three distributions. And these are the closed form solutions for the PDF, the CDF, and the hazard function. This is a lot of math, but I want you to focus on the last column, this hazard column here, because this is the most important thing when you are doing time to event model. If you take a look at the hazard function, the hazard function in the exponential, it's constant. So it doesn't depend on t, it's just the lambda. It's just the rate of the exponential distribution. So this implies that if you're doing exponential time to event, the hazard will be constant. So this is a hard assumption. So just bear in mind that the exponential distribution for you to parameterize your survival function, it's a little bit complicated because you have this hard assumption that the survival is constant over time. And if you take a look at the variable and the comparates, you can see that these formulas, they have a t in there. So that means that the survival function, it can vary. It can either decrease or increase according to the time. So time can remain constant. Oh, sorry, hazard can remain constant over time, or they can decrease or increase over time depending on the different parameters that you parameterize your comparates or variable distribution. And this is the last slide. So this is just a comparison of what I just said. Exponential, we have a constant hazard, so be aware of that. Variable and comparates, you can have hazard constant if you want to. For the variable, you can pretty much say that if k equals 1, that's hazard, or in the comparates, if eta equals 0, that's constant hazard over time. Or if you parameterize k less than 1 or k higher than 1, either hazard decreases over time or hazard increases over time. And in the converts, you can do that with the eta less than 0 or eta higher than 0. So that's the idea. We'll also take questions, but after Lindsay show the code. And for the final slide, it's the different comparisons. So we have three approaches. We have the non-parametric one, we have the semi-parametric, and the parametric. There are some characteristics for the non-parametric. We don't have any, we don't make any assumptions about the underlying survival distribution. So it's unknown and we don't want to estimate or parameterize it. The survival functions aren't smooth. There is a lot of discontinuities, and it's not continuous. They aren't smooth. And it's difficult for you to incorporate covariates. So for covariate modeling, if you want to know if you're interested in the effect of a covariate in the survival of something, of a time to event, you probably won't be using a non-parametric approach. And an example is the Kaplan-Meier estimates, the key-aim curves, as they are also known. For the semi-parametric, we decompose the baseline, the survival baseline function as something non-parametric, so we don't make any assumptions of the underlying survival distribution. The shape can be arbitrary, but we do have some parametric stuff in our covariates. Our covariates, they have some parametric assumptions. And if you don't know how is the shape of your hazard function, of your survival function, but you want to incorporate time varying covariates, then semi-parametric is a good approach for you to do. And one of the major examples is the Cox proportional hazard models, or the Cox regression, what is also called. And finally, we have the full-blown parametric approach, where the distribution is known. You know what the distribution is Weibull, Gompers, or exponential. You just don't know the parameters. The hazard function, you can completely specify it. So you can pretty much do a lot of predictions on that model. So it's a very flexible model and very useful model. You can do lots of stuff. And the common models is what they call AFT, accelerated failure models, or you can say exponential survival model, or Weibull or Gompert survival models, or pick your underlying survival distribution model. So that's how you call them. And that's pretty much it. I think we have just the reference here. And I'm gonna pass to Lindsay so she can showcase the code for you guys.
Thank you. Does anybody have any questions up until this far before we dive into the code? Somebody raised their hand, but it went away. Did somebody have a question? I saw somebody raise the hand, but
someone raised the hand.
I'm not sure if it.
I don't know how to allow them to speak if they want to speak, or maybe they need to type in the question in the chat, or you can also wait for the code and then we can do questions later.
Yeah, I think we'll continue. Maybe it was an error if it has not come back. All right. Can you see my screen now?
Yes, go ahead.
Great. All right. So we're going to go through a single event, time to event model. I have preloaded everything to compile for you, so I might show it off to the side of this instead of showing you in my terminal today. Just know that you can see it in your terminal. I'm just showing you it a little different since I pre-compiled. So today we're using the libraries of Pumas Utilities, Pharma Datasets, Data Frames Meta, and then Chiromachi and Algebra of Graphics to plot. Pharma Datasets is where we're getting our data set from. You will not receive an Excel file with the code in Pumas Labs. It is already preloaded into this library where you're just calling it out. So that that is the first thing you're going to do is you're going to load your data set using the dataset command. The one that goes with this specific code is time to event single. And so I've preloaded it. And as you can see, we have 5 columns of ID, time, dependent variable, event ID, and dose. For the sake of appeasing the read Pumice function down below, when you see we build our model, we need to add an amount column. We're just going to add 0 because it's not going to affect anything that we're doing, but just to prevent an error later on. So to calculate our mean failure time, we're going to use the chain function. And within chain, we're going to use by, which is similar to grouping and combining. So we're grouping by event ID and mean failure to get the mean time. And then we are taking anything that does not have an event ID of 3. And so as you can see, we get a mean failure of 254. Because this data set does not have time units associated with it, you can abstractly think of it as 254 minutes, 254 hours, 254 days, if you'd like. Depending on what you're thinking the event is in this case, it's not specified. And so then we're also going to calculate our mean failure by dose. So again, we're using the by function. Like I said, it's group and combine together. So we're grouping by dose and event ID and mean failure to get our mean time. We're selecting out anything that has a event ID of 3 and creating a new data frame from it. And as you can see, it's now separating it out by dose. In this case, we're referring to dose 0 as not getting the treatment or intervention, and 1 as receiving the dose or intervention. And you can see that they have a higher mean time to failure if they receive the treatment. So next, we're going to convert it to a time series. And again, using chain, we're going to subset the data out to have anything that does not have an event ID of 3. We're grouping by dose and time, and then our total failure to get the length of time. And then order by is, it sorts. So we're sorting by time and dose. And as you can see here, we have a data frame that gives the total number of failures per time and dose, and it's sorted out. If you see, I go to the bottom, there are multiple total failures for the time of 500, which means that the event occurred after the time of 500, which bright censors our data. So we want to remove anything over time of 500. So we're going to use our subset to remove anything over 500. And then we're going to calculate the number of failures. So here we're using the sum, and we get 248. So 248 failures from 300 observations, meaning that they had some sort of event before time 500. And then here we're going to calculate the cumulative sum, or also the survival rate for each dose and group. So we're using group by again, and we're using the functions that Jose had just described in the theory. And as you can see, you will get the dose time, total failure for each time point, and then the survival rate for every observation here. And then we can plot our time series using algebra of graphics. So we're mapping it by time and then our survival function. And as you can see, we will get this plot, which can also be customized if you want to edit, the axes and the title. So as we can see, those who do not get the intervention have a mean survival time of about 150. And then those who do receive the treatment get a mean survival time of about, say, 250. You can actually calculate those values. I'm just arbitrarily eyeballing it here from this plot. I apologize. I said mean survival. I meant median survival. So next, we're going to then specify our models. So again, as I said earlier, we added an amount column to prevent error reading in our data set. So we're reading in the time to event single data set with the column headers that were specified in the data set, in addition to the amount column we added. And once you do that, you'll get a population of 300 subjects with our covariate of dose and our observations as our dependent variable that we specified. And then we have a model for each of the three distributions. So looking at the exponential here, we have the hazard function, the fixed effects, and then the intersubject variability in our parameters. And then we also specify in our pre-block the hazard and the total hazard using the terms from the parameter block. And then in the dynamics block, we are specifying capital lambda equals lambda as, or if the derivative of the cumulative hazard is equal to the hazard. And then instead of using a function here that would be like normal or your error model, you would use time to event using lambda and capital lambda. And then you can fit this model, which I will do right now. And to show you, it might take a minute.
And Lindsay, why do we have to use Laplace I as estimation method?
Because we do not have a estimation for FOCI at this point, so you cannot calculate it using FOCI, FOCE, or the first order conditional estimation. And as you can see, we do get a fit with some estimates using Laplace I for the exponential. The next distribution would be the Weibull. And so again, you have your hazard, your fixed effects, your intersubject variability, and then the shape parameter in this case, which is K or kappa. You would then again specify those in the pre-block here. And then in the bars block, we're going to add a term to time here of a very, very small number to add numerical stability to the model. And again, the dynamics is the exact same, and so is the derived block. And we can fit again. And we're also using Laplace I to fit. And while that is running, I will move on to the Gompers just to show you. Again, hazard, fixed effects, intersubject variability, and then the Gompers shape parameter within your parameter block. You have, again, the shape parameter, the hazard with intersubject variability, and the total hazard in your pre-block. And then you specify in the vars block using your shape parameter and time. Your dynamics and your derived block are going to look very similar to the other ones or exactly the same. And this should run. Either way, I have fitted all these models prior, and so you can see the values that we get from these fits, these estimates for lambda, beta, omega, and kappa. Exponential obviously does not have a shape parameter, so we do not have a kappa value for that. And so then we can also calculate the confidence intervals for each of the models. As seen here towards the right side, it is missing a column. Not shown, but it would show you. And then we would want to just subset our betas out of that. So I did that using R subset to get the betas. And then using R transform from this, I added the model name to the data frame. So on the other side of confidence interval, it says what the model is. And then we can use VCAT or vertical concatenate to create a single table of these values with the names of the models on the right side. And then using the functions that were shown in the tables in one of the slides that Jose had just shown, you can create plots from the time interval of 0 to 100 using the estimates we calculated. We would use AOG, and you will get a plot like this, comparing. So this is time versus the survival function for each of the 3 models that we just showed. Similarly, you could do the same with repeated events. Not much is going to change in this data set compared to single. The only difference really is that you're not going to have beta, as that's not specified in the data set. So similarly, you could calculate the mean or the average event per ID, which in this case is about 2.6. You would add the amount column as well, just so that you don't get the error when you read in the population, and you would read in your population. And as you can see, the models look exactly the same except without beta. And for the 3 models, you still have kappa, your shape parameter, in Weibull and Gompertz compared to the exponential. And if I go down, you can again compare the estimates between the 2, and I have now the VPCs for those 3. So this is for the exponential, this is for the Weibull, and this is for the Gompertz. So with that, do we have any questions? I know I kind of went through some of that a little bit fast. However, it's fairly straightforward.
Yeah, just reminding folks that you'll get the slides and the codes sent to you later today. We will take questions now. If anyone, I just don't know how to open mics, so
I can see if somebody raises their hand, I can unmic them.
if you want to say something, otherwise feel free to type something in the chat. Can you explain the parameter significance, what they mean? And okay, let's go that first. So if you take a look at the three models that Lindsay showed, I think Lindsay, can you share again your screen? Thank you. So what are the coefficients? So what are the model interpretability? I think it's your question. Just go to the chat again. So if you take a look at the exponential, go to the go to the exponential. Let's just take a look at the parameters in the exponential model, in the model definition. Oh, yeah, you can see that. So the lambda I, it's what we call the basal hazard. So that's kind of your constant, your intercept. So we do have the basal hazard in all of those models. Mind you that this is in a log odds scale, so we need to exponentiate that to get odds for it to be more intuitive for common audience. The betas is the covariate effect, the dose effect, the treatment effect. So that is also in log odds scale. So that's why you see a big negative. So that means that the odds are between 0 and 1. So that means that it lowers you having a higher value of the dose, meaning you being in the treatment group, lowers the probability of you having an event. So that's why we have log odds negative. The omegas is the random, the intersubject variability. So it's our omegas pretty much in any PK model. And the k is the shape parameter of the underlying distribution. It's missing in the exponential because we don't have a k in the exponential, but it's present in the variable and Gompertz. And this is model specific. So k 1.4 has a meaning in the variable model, and k, the shape parameter in the Gompertz 004 has another meaning. So that is model dependent. But the basal hazard and the covariate effects, they are the same. And the random effects omega, they are the same in all of the models. So that's how you, that's what the parameters mean. I don't know if that answer your question. And they are in log scale, and they are odds because it's the survival model. So that's how you interpret and analyze them. Now I'm gonna also get another question from the audience, and how how do you judge which model is better out of the three models? Um, First of all, you can do VPC plots like Lindsay showed, but they differ very little. If you want to compare those in a very robust way, you do standard model comparison techniques. You do cross-validation, you do model assessment like AIC, BIC, that kind of thing. Or you do predictions also with cross-validation. So that's how you would assess, and also uh, you would get some domain knowledge validations, like you would say that this model has certain assumptions, the variable model has some certain assumptions, the exponential has other assumptions, and you translate that to a domain expert. So, for example, if you're doing like nausea in, I don't know, in a certain population, like or seizure events, you would translate the assumptions to someone, and someone say, no, no, that's not how work in real life. You cannot have the hazard is not constant. The hazard has to increase, or the hazard has to decrease. So that's the idea. You validate the model assumptions of the underlying distribution with a domain knowledge expert, and you do classical statistical model comparison. That's how I would do it, because I don't understand anything about seizures. That I would call in a domain expert, and I would do also classical statistical cross-validations and other model assessments. Someone also uh, ask what is the significance of small values if lambda is equals 0.002. You need to exponentiate that to get in the log scale. So Lindsay, can you hover over the data frames again, the compare estimates one?
Yes.
So let's exponentiate 0.005. That's 0.005. That's something that um, yeah. So that gives you a underlying basal hazard of you having odds of for every time t, you have odds of 1.005 of having an event. So for you to have an event at time equals 100, you just multiply that by 100, and you get your basal hazard at time t. So that's the idea. Um, which in my opinion, I prepared the code with Lindsay. So someone just asked how to judge which model is better out of all of the three models that demonstrated. Um, I I did not had time to do a pair comparison between those. But if you take a look, Lindsay, could you go down and go into the CIs, the exponentiated CIs, this 3x6 data frame, the
Yes.
online 212? No, the
Oh,
exponentiated one. Yes, that's in logs. That's in already odd scale. So if you take a look, I mean that if you just eyeball the coefficients, that's not the standard way. You would do classical cross-validation and model assessment. But if you eyeball the coefficients, you can see that the variable, that's the model 2 here, does a better job. So the estimate, the standard error of the estimates is lower, and the CI are the confidence interval are also not narrower. I would probably be inclined to use the variable model, but I would compare all of those using classical model assessments that Pumas has, cross-validation, that kind of thing. And I will also do different confidence intervals. We also can do sample importance resampling and bootstrap. I did not do this because the main idea is how do you model time to event in Pumas. There is also a nice question concerning the Pumas team's efforts to combine machine learning with pharmacometrics. Are there any long-term plans for Pumas to allow the use of smoothing functions such as neural networks or splines to predict hazard in the TT analysis? Yes, we do have a long-term goal to do that. We'll probably roll out our deep Pumas, our Pumas machine learning, first in the ODE part, but of course that will also we also roll the possibility for you to define deep learning like snippets of non-linear of functions approximators in your time to event underlying distributions. And we have another question. Why do I see only one profile in the VPC? I thought there were two groups. It's because this VPC is just for the repeated. And the repeated data set, we did not include those. But if you need to have that, you can do, Lindsay, can you maximize your terminal and go over the documentation of the VPC function? So the VPC function, you can do a stratify by. So if you do help VPC, it's just lowercase VPC. Now, as you can see, you do have a stratify by keyword argument, and you can specify an array of symbols. So that's how you do it. If you need to do a VPC that you need to stratify by a certain covariate, that's how you do it. Mind you that this covariate needs to be discrete. So I don't think we support a strat by continuous, like a float, but that's how you do it in the VPC. Do you have more questions? And this VPC will return you a VPC object that you can plug it in the VPC plot function and do customizations, that kind of thing in your image output.
If there are no more questions, thank you for joining us today. Next webinar is in 2 weeks. It's on machine learning in Pumas, where we'll be joined by Dylan, talking briefly an introduction into machine learning in Pumas, the basics. We also have another webinar 2 weeks after that in non-compartmental analysis and bioequivalence. If you have not registered, please keep an eye out for it on our LinkedIn for the link, or if you are part of our subscriber mailing list, that was in the email that came out earlier this week. So with that, I will stop the recording. And if you